It's my pleasure to have Benedetto Piccoli here to inform our colloquium, where you already see the introduction and my previous thing. He's originally from Padua, which I like a lot. And he did the BC and SISA before going to Rutgers. At the end of chair position, he was the regional director at CNI in Rome. So he, in my opinion, he's an expert on control and conservation law, and he's also mathematical deep analysis and to apply to traffic flow, crowd dynamic, biology, and mathematical finance reasoning.
No, mathematical finance long time.
Long time ago.
Biology.
And then, well, he got the Fubini Prize in 2009, and then I had fellow 2012. Importantly, he's the founder of the one important journal, Networks and Heterogeneous Media. So today we're going to talk about control problems for measure evolutions. Please.
Thank you very much. So thank you for this nice introduction. I'm very happy to be here. It's my first time in North Carolina State University. So thank you for hosting me. As you can see, the title of my talk is a control problem for measure evolutions. I promise you that you will see quite a bit of control, but the measures just towards the end. So I'm sorry that the title is a little bit, a lot of control and measures really just for the end. This is a work, ongoing research line, I would say, along which I collaborated with many different people here. I just listed some of those that will contribute to some results I will mention explicitly, but at the end I will provide a more comprehensive list of collaborators. So let's just deep dive into that. The research I'm conducting in the last 15-20 years, many times I try to find like a common theme or a way to present it in a unified way. And the possibility is saying that I study social dynamics of large groups. So what does it mean this? Well, one example that Kai mentioned as first that I worked a lot on and I'm very active now is vehicular traffic. So this is a problem which you have a lot of agents, right? So all the agents with their cars. But obviously it's very different from, say, traditional fluid dynamics. I know many of you are familiar or are expert of fluid dynamics, and indeed fluid dynamics is heavily used in vehicular traffic. But we also understand that it's not a fluid, right? It's not a fluid for many reasons. Some reasons is these agents, the people driving the cars, they are really not passive matter. They really take a lot of decisions, they optimize, they take actions. They are unpredictable. That is one of the big things with traffic. But somehow what comes to the advantage of traffic, where mostly fluid dynamic models are applied, is its specific way in which it is organized. So traffic is not like, for instance, crowd dynamics, where people typically travel in a two-dimensional setting or even 3D setting, with some rules that are set mostly by social conventions. Right? In traffic, you need to follow a lane. Well, at your own risk, right? You need to follow signs, to stop at lights. So there is a lot of much more regulation there. And that, I think, is one of the reasons why it's possible to use successfully fluid dynamics with respect to other problems. I will not talk, or I will just mention network robots and obviously biological application, in particular animal groups. All these are, I see this problem as under a big umbrella. Okay. Now, obviously, each one of these problems do present certain physical characteristics that oblige you to take into account when you're building up your models. But it did happen many times that models designed in one of these areas were moved and reused in the other. So, if we want to talk broadly about the literature, you will see a lot of different fields, different researchers that dealt with these problems. In particular, vehicular traffic, a lot of transportation engineers. Crowd dynamics, you have architects, psychologists, physicists, and other people that were interested in, and you find a very broad literature with contribution of many people. And obviously, again, roboticians, engineers in robotics, and obviously biologists interested in the dynamics of animal groups. So because of this so wide and different literature, you have a lot of different terminology. in talking about characterizing the agents or the agents involved in the system, like words like autonomous, self-prepared, self-driven, self-liquid, void, and many others. Depending on the literature, indeed, void was essentially starting in the computer graphics community, and that transferred to some biologists using that term. But as you see, there is really a wide literature. So I think there is at least 50 years or more history of people proposing models for this system. So what I'm addressing today is mostly their control. Okay, so once you know how to model a system, or you hope to have some models, we know that every model is wrong, but some works well, right? So when you have some working well or reasonably working well model, you can ask yourself if you can control the system after you understood how it works, right? So let me start with a very famous example, the so-called Cochrans Model. It's a second-order model written in the following way. You have a bunch of particles, agents, birds, whatever you want, and you know their position, the position of the ith agent is indicated by xi, and its derivative is the speed, vi, right? And then the model is second order, so you have like a Newtonian-like force, but this is more like social force. So the derivative of the speed of the ith agent is given by what? Well, this is an interaction term with all the other agents, okay? So it sums over j up to n, big N is the number of agents. You have a normalization factor, and here look at what happens. You see, the speed I, this term will push the speed I to align to the speed Vi to align to the speed Vj. Okay? So this is an alignment term. And this alignment term is weighted by a factor that is function of the distance. So in simple words, if A is a decreasing function, you assume that when the agents are more close enough, they try to align their speed. When they are far away, they don't feel that much the interaction. And everything is obviously normalized because if the effect is very big, this interaction could be very big. So again, this model is already referred to as a consensus or flocking or alignment model. Sometimes consensus is used in robots or in sensors where they try to agree on a measurement. Okay? So for instance, you have many sensors, they detect a different measure, and they try to agree on that. And there are algorithms to reach that. In this case, you see they don't agree on the position, fortunately, because the agents don't want to be in the same position, but they try to agree on the speed. So it's very much like when birds are flocking. Okay? They want to fly all in the same direction. Even if, you know, the original justification that Cochrans gave was more to understand the evolution of languages. So completely different thing. Anyway, the specific interaction term they used in their paper is giving to A specific functional form of this type, 1 plus the distance squared to the beta. And then they had the interesting results, in particular, if beta is less than 1/2, that means if the strength of the interaction doesn't decay too fast, okay, at infinity, then you always reach consensus in the sense of alignment. So asymptotically, your group will tend to a unique speed. Okay? That, by the way, is the average. This is not the case if beta is bigger than 1/2. So there is a threshold there. If beta is bigger than 1/2, then you may reach flocking, but this depends on your initial condition. If the group is very sparse in space and speed. Okay? In speed, so that it takes a long time to adjust that, and in space, so that this function may be not strong enough. Then there is a huge literature. Again, the original paper Cochrans Model already gave consensus conditions for beta greater than 1/2. Then there is a very famous cited paper by Ha and Tadmore. They designed the hydrodynamic limit, kinetic and hydrodynamic linear Cochrans Model. There is another very well-known and cited paper by Moshe and Tadmore about local interaction, asymmetric functional. And you know, regarding particle systems, really it wouldn't be impossible to cite all the paper on these many different literature. But again, Reynolds was the guy from computer graphics that started to talk about the designing program, and then he went to work all the way with Sony for movie production. You know, when you see those large crowds moving around, it's obviously a computer creating those, and he worked for Sony for many years. Bitschek is a physicist that designed a very famous model, and these are many other models. Krause, Cousin is a biologist, Helbin worked mainly in crowd dynamics. And on the math side, you have a lot of big names that work in this area and work specifically on the Cochrans Model or other models. In particular, in passing to the limit, like the work of Hatta. Okay, let's now move and say that we want to control this system. Okay, so we assume that we have a control term here, UI, for every agent. If you just add UI in that way, you ask the usual question, is the system controllable, optimal control, and so on, you're doing something probably not very innovative, and also that maybe will not apply that much to the application that you have in mind. Because if you want to control a large group, say in traffic, it's unlikely that you will be able to give instruction precisely on what to do at every driver in a centralized manner. Okay? It's much more likely that you would be able either to do planning, like, you are constructing, for instance, robots interacting among them, and you can design offline a control mechanism by which they act in a feedback way. Or it could be that you act real time on the system, but just on a very small number of agents. That is much more likely to happen, rather than you have, a classical centralized complete control. So that's why we try to understand things more in this setting. Now I will talk about some control results. The main people involved were Marco Caponigro, Massimo Fornazier, Francesco Rossi, and Emmanuel Trellat. But there are a lot of people that worked on the consensus side from the engineering perspective and control program related to that. This list is obviously incomplete. Okay, so our idea is we want to control the system, but in a sparse way. By sparse, we mean that we assume we are able to control a small number of agents. So let's start to set up a few mathematical terminology. So we call VF, say, the consensus manifold, where the system drives naturally, at least if the interaction potential is strong enough, and by V orthogonal, it's orthogonal. Then there are one functional that is very useful to understand the dynamics of the system, is this bilinear functional. You see, it's a kind of covariance, if you want. And if you apply it to the vector x-axis, it measures exactly how much sparse is your group in space. And if we define the function v to measure the sparsity in speed. Okay? So our aim is to drive the system to alignment, so to this manifold VF, flocking one. Already it's easy to give conditions on the interaction functional and the sparsity of the group, ensuring flocking. And this condition reads in the following way, you see. You look at the initial sparsity in space and in speed. Okay? And you want the sparsity in speed, the square root of it, to be dominated by the integral between this square root of x0 infinity of what? Of the interaction functional, was this A, integrated from square root of x0 to infinity and another normalization term. So this essentially measures how much strength of interaction is still available for your group, even if your group is, going far away in space. And this is the sparsity in speed. So it's a reasonable condition. It says that if there is enough interaction potential that will drive your group together, that dominates the sparsity in speed, you will be able to flow. So it's a reasonable condition. And it's reasonably tight. What I mean is that if this condition is true, you're going to flock. If this condition is false, no one proved that a strict inequality will prevent flocking, but numerically, apparently, is what happens. Yes?
Does this include the case of beta greater than half?
Absolutely. So indeed, it's interesting in the case beta greater than 1/2, because if beta is lower or equal than half, this integral is always plus infinity. And so this equality is trivial. And we recover the...
So you don't need control?
No, absolutely.
Okay.
That's a very nice observation. Okay? If beta is lower or equal than 1/2, this integral, independent of the square root of x0, explode is plus infinity, so this condition is empty. You always have flocking and you don't need to control. The interesting case to control is exactly when beta is greater than 1/2. So in that case, the interaction potential is not strong enough. There are initial conditions for which you wouldn't flock, And there is where it's interesting to introduce the control to induce flocking. Thank you for the question. Very nice. So there is a first trivial thing we can do. So imagine to be in the condition beta greater than 1/2. So we don't have automatic flocking. So there is, if we take the centralized point of view, so we assume that we can act on every agent, then there is a trivial control that induces flocking. That is essentially you look at the orthogonal component of your vector of speed. So you see how much you are far away from flocking. And you just drive the system in the opposite direction. So pretty trivial, right? So if you can do something centralized, whatever is alpha, so you don't need even big control, you're gonna drive the system symptotically to consensus over flocking. So, are we just reinventing the wheel, not doing anything really new? Well, if you read the control literature, there are techniques when you have a control-affine system, so a system that could be more complicated than ours. And if you know that the uncontrolled dynamics admits a Lyapunov function, and this is exactly the case of the sparsity in speed, is a Lyapunov function, then there is a very well-known technique since the 70s called Jurjevic-Quinn feedback. You essentially move, like for the specific example there, against the gradient of your Lyapunov function with your field in control, and under certain conditions you can prove that this leads to stabilization, or in this case, consensus. So, and there are many results, let me cite just one of these, that generalize this technique to any possible extent. This is an example of a generalization in the case in which you replace the control system with a differential inclusion, in which you ask the usual minimal assumption, upper semi-continuity and anti-contact complex values, and you use some type of generalized derivatives. But there are so many results. You can find Jurjevic-Quinn in any type of flavor you want. Just look at the literature, and there are obviously deep results there. So, if you're interested specifically in this type of techniques, there is a very nice book called The Lyapunov Function Stability Control Theory by Bachelor and Rossi of 2006. But we want to do something different. We want to do centralized control. We want to do sparse one. So the way we acted is the following. So you see, we try to solve instantaneously a problem that will induce consensus or flocking, but also induce sparsity. So every one of you knows that sparsity is linked to the L1 norm. So what we are doing here is exactly the following. We consider this function. Take a look. V is the vector of your speed. U is your control. So trying to minimize this part would indeed try to induce flocking. And then you have another term, you see, where the gamma is similar to the one that you saw in the previous slide, is this integral. And then here you have the L1, L2 norm of the controls. So L1, L2, because you see, you sum over the components, that is over the agent, but then for each agent you take the L2 norm of the control. Okay? Now every agent may evolve in any, say, RB, so that is the usual Euclidean norm. So this is called L1, L2, right? Because you sum over agent, but then you use them. Okay, this functional works well in the following sense. First of all, there exists a minimum for any xb, there exists a solution to this problem. And then using these controls, you can define differential inclusion. So the solution may be not unique. So indeed, you identify many controls that are solution to that. So instead of defining a unique control system, you define indeed a differential inclusion using all this solution. And if you look at trajectories to this differential inclusion, then they converge to consensus. Okay, so this is one way of solving the problem. You set up a functional, there are solutions to this function that are instantaneously computed, and then the solutions in a Filipov sense of the differential inclusion will tend to consensus. Now, this is not completely satisfactory because you see some of those controls that solve that problem may be not sparse indeed. So you induce sparsity, but if you pick up randomly one of those controls, could indeed interact on many agents. So one way to solve that is simple. Well, essentially you do some kind of lexicographic selection. So the way you do is the following. If you have this inequality That means that you have enough interaction strength to flock, then you choose just a zero control. If you need to intervene, then you look at the controls that have, the edges that have the maximal far away component from consensus, and you just act on that edge. So the downside of that is that now is a single valued control, but is very highly discontinuous. It has crazy discontinuities, any type of difficult discontinuities. So the way to handle that is to do sample and hold techniques. That is the following. So assuming you define this very discontinuous control, then you fix a parameter for any initial condition. There is a small enough sampling time so that if you use a sample and hold technique, you convert to consensus. Sample and hold means I read my control, defined in this way, and then I keep it constant for an interval of length tau. And then I resample and so on and so forth. This technique is called sample and hold. And the limits of these sample and hold solutions are called the Clark-Ledeyev-Sontag-Subbotin solution. So both from numerical point of view or practical point of view, the sample and hold works, and also from an analytical point of view. You can define formally their limit, and their limit are well defined and they work well. Another thing we can say is that this functional that induce sparsity is somehow optimal in the following sense. So if you look how fast is decreasing the Lyapunov, the natural Lyapunov function, then this is indeed decreasing as fast as possible with this control. Okay. So it's a kind of optimal for decreasing. So in that sense, it's a greedy control. It aims at decreasing the function as much as you can. Obviously, you know that globally, this may not be the optimal control. Because if you have a greedy technique in any control problem, may not be the global optimal. Okay. It's very hard to do the optimal control complete analysis. You can write either the Hamilton-Jacobi equation that Kai likes very much, or you can use Pontryagin maximum principle, but those systems are typically very highly dimensional. You want to consider a lot of agents. So it's not that easy to manage those equations. So this is a little bit of simulation. You see these are the speeds of a group. So the red case is that they are uncontrolled, Cochrans Model. So you see they don't converge to a value, and the blue one are the control. You see that when there is a change in slope, it means that the control is acting exactly on that edge. And this is the trajectories in space. So you see the uncontrolled one, they will continue just to go far away, and the control one, the blue one, they will quickly align and go toward to flock. So summarizing, the results obtained in 2-3 papers are the following. Well, first of all, you have trivial stabilizing control if you have a centralized policy, but you can design component-wise sparse control. You can also have time-wise sparse control using this sampling technique and obtaining solution in the sense of Clark-Ledeyev-Sontag-Subbotin. Sparse is better principle in the sense that it's a greedy control. Well, so it's better in the sense of greedy. Controllability 2 and consensus manifold. I didn't talk about that, but you can prove various results on local controllability. And finally, that technique of Jurjevic-Quinn control, you can indeed extend. You can design sparse control under that technique. So it's not limited to Cochrans Model, but to any system that would allow the Jurjevic-Quinn approach. All right, so Kai mentioned a few facts about me and my career, and he mentioned something that I do a lot of applications. So I show you now a real application of doing sparse control. So this is not exactly like a warning. Obviously, I'm cheating a little bit in the sense that this is a research that we did in parallel with studying the Cochrans Model. We are not applying exactly the sparse Cochrans Model. Okay? But we use similar techniques. So first of all, a little bit of background. This is a very famous experiment in the traffic literature that people in Japan used, and is a famous one of waves being produced in a perfectly symmetrical solution. So this car started equispaced on a ring, and because of oscillations in human driving, after a little bit, one decreases speed a little bit more, the other one reacts faster, and so on and so forth. After a little while, you see there are waves that are produced. Oh, I don't know what. Oh, because I used that, I guess. So I will be careful not to repeat. But there are waves that are moving around. You can see this. Yeah. But can you see the wave? So they stop and reaccelerate. And the wave, that is the point at which they go to almost zero speed, is traveling backward, you see. That is a true shock wave. So can be detected with conservation laws models. Okay. So you see the shock, and it's very clear the shock. We did a lot of experiments to confirm these Japanese experiments, and it's really ubiquitous. When you have enough cars on a circle, it always happens that these waves show up. So, you know, we are talking about control, so obviously what we did is that, okay, you know that the future of driving is autonomous driving. Well, autonomous driving could be all the way to a complete robot that drives, takes a decision for you, but you know, there has been some slowdown also due to famous accidents that happened in Arizona, so now people prefer to talk about increased autonomy. For instance, there are the intelligent cruise control on board of many cars, and the idea is that that is a first level of assistive driving. So people don't talk anymore about the computer will take your place, but the computer is helping you drive. Okay. So we thought, okay, there would be some form of assisted driving or autonomous driving. So can we take advantage of that to eliminate this phenomenon? And how important is this phenomenon in terms of safety, fuel consumption? So these are the experiments that we ran in July in the Arizona desert. Don't ask me why we went there. Anyway, this is called the dissipation of stop-and-go traffic with the control of a single autonomous vehicle. This is a joint research of University of Illinois Urbana-Champaign, Rutgers, Temple, University of Arizona, and Vanderbilt joined at the end. So here is the setting. We created a setting, you see, that is very similar to the Japanese one. Okay? Here is my postdoc and one investigator from Urbana-Champaign that had a big horn to start the experiment. It was a very important role. So the experiment starts, and you see, let me immediately stop. You see the cars are turning around, and the big arrow indicates the car that has a computer on board that is capable to do autonomous driving. So the computer is capable to take complete control of the car. When the arrow is black, then the car is human-driven. There is also a human on board that is driving. It was indeed a trained pilot, just to be on the safe side. And then when the arrow will become red, that's going to be when the autonomous driving will the robot or the computer will drive. So what happens is that we waited some time, and as expected, the waves start to show up. You see now there are these big waves. Let me stop now and let me tell you a few things. So you see, what is represented down here is the speed of the autonomous car in black, in gray of all the other cars, and this is time. So clearly the wave in that graph is represented by these big oscillations, right, in speed. And up there, you see now the computer will enter the picture. But up there, look what happens. We measure the velocity standard deviation, the fuel consumption, the braking events, how many times someone decreased by more than 1 meters per second over a period of a second in speed. And the throughput means the number of vehicles that will pass through a point, the flow, if you prefer. So you see, immediately look how dramatic is the effect of the waves. Without the waves, you see the velocity standard deviation double. The fuel consumption had an incredible increase. The braking events, you see, multiplied by 4 or more. The throughput, though, may even increase. Okay? The throughput is the variable that is less influenced by these waves. So, you know, there are a lot of braking and accelerating, but the number of cars at the end is very simple, passing through a point. So now the computer will start, and we start to perform some algorithms that, you know, are similar to the flopping one. The computer is trying to give a little bit more of headway and making enough space to cancel the wave. So after a little while, you see the weight is essentially cancelled. But look at the number up there. They start to be impressive. Look at the fuel consumption. You know, we tried various different target speed, so there are different effects. Let me stop one more time. I promise the last stop of this move, of this movie. So we targeted various speed, and we have different behavior. But you see that we essentially cancel the weight for most speed. Interesting enough, this speed and this speed and this speed were good. When we target a too high speed, we somehow induce other weights. So there is some decision to be taken there. But look at the number. Fuel consumption went from 24 to 14. So we had more than 40% of the fuel consumption improvement. This fuel consumption is not fuel consumption estimated. It's measured with real onboard technology. This is very important because many times people come up with models to estimate fuel consumption that could be really not that reliable, but this is measured directly from the OB2 car.
In the control, maybe it's the solution when you control still some shock, right? Or without shock. When you
This is you see completely in an ODE setting, not in a conservation law. When you are in a conservation law, obviously analytically things become more difficult. This one, as you see, we have a small number of cars, so we solve the problem at ODE level. So, and also technological wise, guys, I don't know if you ever worked in an experiment like that, but we had a few months of preparation of experiment like that. You have to overcome difficulties like finding the place, finding the driver, safety, permissions, any type of thing. So I don't know if you have been involved in such a kind of things, but believe me, it takes huge effort and amount of time, and there are so many things that can go wrong. We were working an average of 18 hours per day during the experiment time, and we were there for 1 week. And that was really strictly necessary to make it work. Yeah?
Can you, I think I missed this. So what are you controlling? Like what
The
is
speed of the autonomous car.
Okay, so just the automatic that just goes to a certain speed. Given by, you're minimizing what cost?
Very
you have
good
to
question.
figure out
So
the
indeed,
control.
we are not minimizing a cost. We designed a few batteries of control that were, okay, so we are entering a little bit too much technology, but let me tell you how it works one of these cars. So one of these cars have a computer board that can control the speed, but we left the steering to the driver because it was anyway on a circle, so was not much to do there. The control is computed based on the knowledge that the car has, that includes its position, speed, and the headway. It has a laser on board that can measure the headway in front of it. Okay?
How much space it has
How
to
much
the
space
next
the
car.
headway to next car. Okay. Based on that three parameters, we designed 5 different type of control algorithms. And the reason is that, don't think that you just tell the car what to do. The car is a very complicated machine. You need to design a control. The control is translated by a couple of interfaces by the computer, and then is given as a command to the car. Now, interesting enough, we assumed that many times, for instance, with the mathematicians, as the mathematician side, we designed the acceleration controls, right? We thought that was what we do. But they cannot be essentially implemented by a computer. The only way to do is you prescribe velocity profiles over a given time interval, and there are 2-3 software in a row that will try to follow those profiles.
So you couldn't follow the equation V dot equals something plus U.
No, we do. We can do, but the way which control is way more indirect than assuming you control. So if you design a control, just assuming that you can control directly the ODE, that once you try to translate through all the technological steps, will end up probably in something crazy. So you design taking into account all the different things so that you don't act directly on the equation. There are some steps there. You rather should predict the velocity profile that will work, and you need to take into account all the technological burden that includes a lot of delays and errors. So that becomes, you see, I'm hiding that part because it's not so interesting for the math department, but for engineering perspective, you could just do a seminar talking about all the technological steps to overcome to do that. But essentially, morally, you control the speed of the autonomous car. So if you look at numbers, especially at autonomy 750 meters per second targeted, 40% decrease in fuel consumption. Look at the braking event from 858 to 0.12. Okay, you essentially cancel the braking events completely. Now, people are very careful at connecting braking events to safety because almost everyone in the field believes that they are strongly connected and there is some evidence, but there are not enough data to make a complete claim. But by direct experience, a lot of incidents and accidents are more, probable to happen if there is this speed variation, right? If cars drive at the same speed, it's much less likely that an accident will happen. So we cannot claim complete safety, but braking event for sure. Okay, so this is then the end of the experiment. We then finally switched off autonomy, and we saw that after a little while, the waves were naturally reappearing, okay, as soon as we were switching them. Okay, so I hope I convinced you that there is possibility of applying this stuff to real problems. We did our experiment this summer. This is summer of 2 years ago. We did some other experiment this summer with the autonomous cruise control, and the result will be available soon in a paper. And we just wrote a big NSF project to do control over a whole stretch of highway. That obviously even more will bring all the technological burden, but we got Berkeley on board. They have a fantastic center, a lot of autonomous car. They are very well connected with California DOT, so we can go and do whatever we want on a highway, but in a safe way, obviously. And so that is what we are aiming for. So let's go back to math, okay? And let's ask the same question. Can we really control these systems, or we are just playing around? So we know that, let me rewrite the system in a way that is maybe familiar to anyone doing kinetic system. So we write the system with the empirical measure. So the empirical measure is like you place Dirac masses in the position where the agents are. You generate in this way a measure, and you can write the evolution with the convolution operator with your measure. Okay? So if you want to, you just write in a different way. But obviously what you want to do is then pass to the limit in the classical sense of kinetic limit, and then you have problems like proving propagation of chaos. And obviously, these are just to name Koch and Brushin, but obviously there are a lot of people that work on that. Typically, you aim at obtaining, in the best case scenario, where you don't have collisions, a Vlasov-Poisson type equation that is like a transport term plus another term for the stuff. Okay, that's what you typically obtain. So can we use these same ansatz for control? So, because when the number of agents grows very fast, it's essentially impossible to design analytically, sometimes even numerically, this type of controls. There we were controlling one agent, but what happens when we will go to the highway or we will go to very large systems? So obviously mathematics helps passing to the limit, but where can we pass the limit also in the control? Then think about it. Well, we will have an equation of this type with this control. Okay? And then formally we can pass to the limit. We will have still the Vlasov-Poisson system, but there is a term here. Okay? This term here is somehow the limit of these controls. But there are a lot of problems. One of the problems is obviously that those limits work well when there is indistinguishability of particles. So your control should act in a way that is not particle distinguishable. And this creates already a huge problem. And the second problem is that if your control is not well designed, in the limit you may typically achieve a measure that is completely orthogonal to mu. If the measure mu is orthogonal to mu, you're essentially in the limit doing nothing. My friend Massimo Fornazier likes to talk about this problem with an example. Assume there is a river. Oh well, first you design your control that is like, in a small creek to put a large beam, say, and you affect the flow. But then you start, to go to larger river, and you have a bigger number of beams, smaller and smaller. Then this would be like taking a billion of toothpicks and trying to control a river. What happens is exactly that. Your control could become orthogonal, and so even if you use a billion toothpicks, they will do nothing over your river, right? So that's the type of problem you encounter. So there are some solutions. One type of solution is the following. Well, you know already that you are not going to be able to control the whole set of agents. So you select a small number of agents that you call leaders, because they're the one that you will be able to act upon. And so you rewrite your system, you see splitting into population if you want. The leader that are controlled, and the bulk population that is much larger and is uncontrolled. Clearly you have the cross terms. This is the bulk population, these are the leaders, and so they appear on both equations. In this setting, you can pass to the limit, but obviously only not in the leaders, but you pass to the limit in the bulk population. Okay? And then in this case, you see you have still a bunch of ODEs, but coupled with the Vlasov-Poisson equation. This approach works very well in the following sense. If you define the approximating functional, the one when you have a big N equation, and the limit one, the one in which you have the Vlasov-Poisson equation, then you have gamma convergence of the functional. So in particular, the optimal controls of one weakly converge to 2. So one possibility is that one. You restrict to a small population of leader. In that case, you can pass to the limit, and so you can design controls that to the limit will have to have on your system. Another possibility, obviously, is just start from a limit equation and trying to impose constraint on your control that can be used, like a small set of small fraction of population to control that. We run both approaches, and they work well in terms of achieving the expected result. So you can control the system, you can reach consensus, and so on and so forth. We mentioned, so Dobrushin work in passing to the limit, okay, to the Vlasov-Poisson. So I don't know how many of you are familiar with Wasserstein metric. So before introducing my last approach to this problem, I would like to refresh your mind or introduce the Wasserstein metric, depending on how much familiar you are with that. Let me start with the cartoon. So the conception of the Wasserstein metric is the following. You have two measures. Assume, for simplicity in a cartoon, they are a set of small cubes, right? And you want to optimally move one set of cubes over the other. Obviously, you assume that you have the same number of cubes, okay, on the two sets. And then optimally means that, you will find a strategy to move each cube from the blue pile to the green pile in such a way that if you sum up all the distances covered by moving this cube, this is minimal. Okay? And this is called the optimal transport or Monch-Kantorovich problem, and the distance between measures so generated is called the Wasserstein distance. Okay? So it's a completely different way of conceiving your problem. You see, when you use the L1 distance, you are measuring vertically your distance. When you use Wasserstein, you are measuring horizontally. So you are really switching mind about how you consider the distance among your measures. We are mathematicians, so let's go for the true meat. And how you define that? Well, the way in which you define that is the following. First, the problem was proposed by Monch in 1781. So you see, you have two measures, mu and nu, and you look at all the maps that push forward one measure over the other. Okay? Push forward means that if you take pre-images, one measure corresponds to the other. And you fix a cost. So, for instance, the distance to some power p. Then you look at the infimum over, you see, these are the distance run by every mass. If a mass is at x, we'll end up at gamma of x. So if the distance run by your little cubes to the p, and integrating with respect to the first measure, obviously, because that is the mass that you are moving. And then you put a 1 over p, when you have p norms, you always place with p and 1 over p, right? To have a good norm. So this is the p Wasserstein distance. Indeed, it's not the Wasserstein distance. Why? Because if you restrict yourself just to maps, so true maps, say measurable ones between the space and itself, you will not get an infimum here, because in general you don't have any map doing that. A very simple example is the following. Take a measure mu that is a single delta centered at the point, a measure nu that is 2 delta of weight, say 1/2, displaced somewhere else, then obviously there is no map that map the first measure onto the second one. But there is a trick here. What we want to say is that if we look at the product space, if we put the measure on one side and the other on the other side, oh sorry, I don't know why there is a 4, 5 here, but then there is a way of mapping one measure into the other. That would be this. So I take this mass and a split in two pieces, right? This is not realized by a map, but it is realized by a probability measures on the product space. Okay? You design a probability measure on the product space so that on one side project on your measure, on the other side project on the other, and this is equivalent to say is a formal transport. Okay? Or if you prefer, you allow yourself to spread the mass. You take the mass and you split into. This is where realized by a probability measure of the product space, and so this is the way in which you define. You call transverse plan a probability measure of the product space, and then the minimum is defined, taking the minimum over all these transverse plans or probability measure over the product space. This is gives rise to what is called the Basel distance. Obviously, you heard about optimal transport and all the huge success it had with the two field medals assigned in recent years, right? First to Cedric Villani and this summer to Alessio Figalli, both for mostly work in the area of optimal transport. I recently introduced the idea of defining the evolution of measures that would be based strongly on this distance, and the idea is really to provide an alternative method. I mean, it's not a Lagrangian flow, it's not a gradient flow in Basel spaces, those are very important too. What I'm proposing here is rather to introduce a natural measure generalization of ordinary differential equation. Let me show you how this would work. So first of all, let's rethink what is an ODE or a vector field. So a vector field is something that, well, let me talk about base and fiber, like if we are in a tangent bundle, but think to what is an ODE or a vector field. A vector field is assigned to every point in the space, a point if you want in the bundle because it's a tangent vector, right? So it's just a map, it's just indeed vector fields in geometric approaches are seen as the sections of the tangent bundle, right? So, okay, so we have this geometric representation. Why don't we interpret it as measures, taking the natural immersion between Rn and the space of probability measures over Rn, associated to every point the Dirac mass centered at that point. Okay? So your vector field is nothing but a map that associates to every Dirac mass, another Dirac mass on the tangent bundle, so that this Dirac mass lies exactly over the other. Well, this is necessary, right? Because if I assign a vector somewhere else, this has no much meaning. Okay, so I naturally generalize by saying that a generalized vector field or a probability vector field is a map associated to every measure, a measure on the tangent bundle, so that it projects down to the original measure. And so here is the definition. A probability vector field is a map from the set of probability measure on Rn to the set of probability measure over the tangent bundle, so that if you use the natural projection of the base, you get back the measure. Obviously, let's skip for a moment all the technicalities, a little bit of measurability, regularity, and so on, but that's essentially the idea. Can we define a solution? Well, obviously, a solution could be interpreted in which sense? What is the meaning of this d of mu? Well, if you look over every point here, at this point, we cannot talk right about the value of the measure at the point, but assume that, we identify what does it mean, the mass here. Up there, these are the speeds along which your mass is spread. Okay, that's the idea. So I can define a solution in a very nice, weak way. So the derivative of my measure against any test function, you see, spread around those speeds. That means exactly that it should act as the gradient of f dot v, where I integrate in dv mu t in the tangent bundle with respect to x and v. Okay? So x is just entry here, and v is integrated according to my probability vector field. This gives rise to a concept of solution that is extremely weak. In particular, you can replace this by its average, and you still get a solution. So existence is very easy, uniqueness is way more difficult. So existence can be obtained in this general setting, but very natural assumption. These are, I decided initially just to do measure with compact support. So to get rid of all a number of technicalities. So if you set yourself in that setting, then you see, it's very easy to obtain existence of solutions. You just get some kind of sublinearity like you have for ODEs, but now you write in terms of the support of measures, and you have continuity. So this is the equivalent of Peano theorem. So some form of sublinearity and continuity, you have solution for every time. Obviously, you can do a local version and all the variants that you want. But what about uniqueness? Can you address uniqueness? Because if you have equations for which you prove some existence, but you have no hope of uniqueness, then not that big theory. But fortunately, you can prove uniqueness. You cannot prove uniqueness at the level of a single solution. There is no hope. It's a two-week concept. But you can prove uniqueness at the level of a Lipschitz semigroup. So at the level of Lipschitz semigroup, what means is the following. I can prove that under certain regularity, there exists a Lipschitz semigroup of solutions. And if you impose the Lipschitz semigroup to be close to a Dirac germ, that I mean a small time evolution for finite sum of Dirac masses, then the semigroup is unique. So it's a little bit like what happens in conservation laws. Conservation laws, you introduce weak solutions, you don't have uniqueness. You can have uniqueness of semigroup that are compatible with a given Riemann solver. That would be a given way of solving special problems, the one that have a Hill size function as initial condition. Right? So this is similar. So we call Dirac germ, small time evolution for finite sum of Dirac masses. We say that the Lipschitz semigroup is compatible with that if it's close enough for small times, and then I can prove existence and uniqueness of a Lipschitz semigroup compatible with a given evolution. The last technical point is this is the condition that ensures uniqueness. So let's just read that. This is not a distance. It's a function. I need phase to be a distance because it phase the triangular inequality. But the look is the following. I take two probability vector field if you want, but here in general are just two measures over the tangent bundle. Okay? And I look at this quantity. Look, I take a transferent plan between these two measures, like I would do in a normal Monch-Kantorovich problem, but it's just up in the tangent bundle. And I compute this part. You see, this part is the usual Monch-Kantorovich distance, but it's just over the fiber. Okay? I don't care about the base, because what happens on the base, I require that its projection on the base is optimal with respect to the base projection. So essentially, you should imagine that those are two probability vector fields. So they lie over their base measures. So I don't want to move in any possible way this vector field, because I could mix vectors that are lying over some, I could mess around everywhere in the tangent bundle, but I don't want to do that. I want to restrict myself to the plans that on the base are optimal. So move optimally one measure over the other, and then only for those plans, I look how much they move around things over the fiber. Okay. Since I do this, say, non-homogeneous restriction, this phase to be a distance. It's not a distance because triangular inequality is false. But this condition is exactly the one, Lipschitz continuity of this quantity with respect to the vector field is exactly what you need to have uniqueness of this Lipschitz semigroup. I hope I scared you enough, so my last slide is just devoted to all the many collaborators I told you that helped me in all this research. They are divided by the different areas they worked on with me. I didn't talk today about supply chains, crowd dynamics, and other fields, and some of them, worked on multiple fields. So it was a nice problem to solve to try to find their spot so that they appear in every circle they worked on. Maybe not every set is designed perfectly, but my biggest thanks goes to them. Many of them are smiling. So probably they had a nice time doing this type of research, and similarly, I hope you had a nice time listening to the seminar. Thank you very much.
Are there any questions?
So I'm just curious, so the controls that you create, are they seem like sort of adding diffusion to the system in some sense? I'm curious.
I would say the opposite. You intend the Cochrans Model or the traffic ones?
Well, so I'm thinking like in general for conservation laws, if you want the shock wave to go away, you'd have to add some pretty strong diffusion.
Yes and no. It depends on how you apply the control. Typically, we can define the control system for conservation laws in many different ways, right? There are boundary control, there are diffuse control. These one are what are called sometimes Lagrangian controls, because you have a sparse number of particles that you want to control. And anyway, when you want to pass to the conservation law control, you need really to use mixed systems, ODEs, PDEs, where, for instance, what's the meaning of controlling a single particle in a conservation law? There are possible ways of giving the meaning. One of the ways we use is that there is a pointwise constraint on the flow. In that case, you have a coupled ODE, PDE. It's a bit delicate because you need to prove, a good theory. We just proved continuous dependence for this type of systems with a lot of difficulty this year. And not necessarily you introduce diffusion.
I'm also just curious, when you actually solve the optimal control problem, do you pose the Kuhn-Tucker system, or do you do the Lagrangian?
No, as I said, we are not able to solve the true optimal control. So, for instance, this type of sparse controls, they are greedy controls. They solve finite dimensional problems at every point. They are not optimal control one. If you write the Pontryagin maximum principle for those systems, or Kuhn-Tucker or Lagrangian multiplier, there are different ways of using names, but they are the same idea. In the control community, you refer always to the Pontryagin maximum principle because it's the most general tools to deal with that. You don't get much out of that because it's too complicated. Pontryagin maximum principle provides you detailed information on the optimal control in special cases. For linear system, for system with a lot of structure or in low dimension. But in such a high dimensional linearity, Pontryagin maximum principle, I wrote a whole book on how PMP determines all the optimal synthesis dimension 2. And we know that in dimension 3 already, you're not gonna go that far. So yeah, it's possible to do something, but not at the level of solving the optimal control. That's too much. You're welcome. Ali.
Yeah, I have a question about the next step. Would it make sense, in principle, the next step to generalize the model like doing maybe two-way traffic or looking at distance or multi-class traffic, things like that?
All what you said. So, yeah, in the following sense. Let me address that. Multi-class, absolutely yes. Because when you are doing something like leaders, we are exactly doing a multi-class type. We are looking at models that stay at the conservation law level, so dealing with that. Unfortunately, the theory of conservation laws, when you enter systems and multi-class and so on, is tough. Sometimes you lose hyperbolicity at some point. It's a mess. I mean, analytically, it's a mess. We are trying to do multi-class with the Vlasov-Poisson type limit. So we assume a little bit of diffusivity in that case, yes? And so we assume we can pass to the limit in a Vlasov-Poisson sense. And at that point, we are trying to use control on the Vlasov-Poisson. The fact of enlarging to highway is exactly what I mentioned. We are trying to work with engineers at Berkeley and trying to push it that way. Two traffic directions is really a different animal because in principle, drivers on one side are not influenced with drivers on the other side. In principle, in the sense that when there are accidents, everyone knows that traffic accident on one side affects traffic also on the other side. But in normal situation, typically they interact with each other.
But what I meant maybe not two-way traffic, I mean multi-line.
Multi-lane, no, absolutely. We are going to the multi-lane.
Because it becomes multi-dimensional.
Absolutely. So what happens there is the following. There are multi-lane models at the ODE level, and they are already complicated enough. To my knowledge, there is not any good model at conservation law level with lane changing. And again, because you will get one equation per lane with the interaction between the lane, it's hard to manage. What we are trying to do is rather do multi-lane than Vlasov-Poisson. That seems more
Any other questions? Okay, let me answer the last one. Because we said about the measures one. How could you go far from that direction? Should be something new, right?
Sorry?
About the last slide about the measure one.
The measure differential equation. Yes. So
How far can you go?
How far can you go? So wherever you want, right? No, it's so up to now. This theory I wrote a preprint last year, and we wrote another 2-3 papers. Some are already available, some are under the way, and nothing is yet published completely. I just received the review for the very first paper that hopefully will be accepted, and we are submitted. So it's very early stage. I already thought about how to address control in that setting. And I wrote a paper that is going to appear to the Conference on Decision and Control now in December. And in that case, I really tried to mimic what people do in differential inclusion. There is really a major obstacle there. So one ansatz that you typically do in differential inclusions is strongly based on the convexity of the unit ball. And the convexity of the unit ball fails in the space of measures in whatever sense you want to give it. So all the major techniques there collapse. You can do something, but I think that is a hard way. I wrote one paper that's a hard way. So what I'm trying to do now is really to go the other way. So think not really as a differential inclusion, but rather think to put control, for instance, at the level of operator. It's very well known in control theory that you can either control directly the equation or look at the flows and try to control the flows. Assume that you are controlling the flow. So you are flowing in one direction and then in another. So you are like doing control of different morphisms, if you want. And you end up quickly in what is called the chronological calculus that was mostly set up by Andrea Grachov and Radon. But by the way, was one of the co-authors. So I think that a more promising direction there is go that path. I think that the differential inclusion one, there are too many obstacles to be overcome. In the direction of a chronological calculus is possible, but obviously even there, you don't have in the space of measure with the passage distance the nice linear structure of a vector space. It's just a metric space. So there are a lot of technical difficulties to overcome.
Yeah, I'm asking because the outcome before the Antonio and you work in some case pass into the continuity equation and then
yes, in the case of work with Antonio was not based on measure differential equation, but was based on writing measure evolution starting from the ODEs. But it's somehow.
Thanks.
Thank you.
Any other questions? Otherwise, let's thank Benedetto again.